rather than, so here's our first error. You have the answers in front of you. Step 02, line 30, years is not defined. So I'm tempted to, I say 2 years. That looks reasonable. So how would I know? So that's the question, is that in terms of units, how would I know what units are available? This is a PIRE feature. That's a framework that's sort of not very well documented. So the I don't know if in the manual we put the list of units for length, time, and so forth. We should. But here's how you here's the trick that I can use to find out what units are available. So I'm going to load up the Python interpreter and do import PIRE units time and tell it what units do you have. So it knows day, hour, microsecond, millisecond, minute, abbreviation for millisecond, nanosecond, picosecond, PS for picosecond, S for second, US for, I think, microsecond, and then year. So there's how I could get the list of units. I can do the same thing for length. And it can tell me all the units of length that it knows. You can do nautical miles. If you want to make your mesh in terms of, or light years. It's sort of meant to have all sorts of units. So that's what we want to fix. So let's load this up. So it was line, I think, 25. We're down here. So year. So that's our first fix. Well, that's, yeah, I had a time, length, pressure. I think, I don't know. Let's see. Is it? It knows pressure. So it knows atmosphere, bar, giga, kilopascal, kilo, watt, mega, millibar, pascal, torr, and it knows abbreviations gigapascals, megapascals, and pascals.
Like, is there any way to know that your variable total time is time? I mean, that's really general, but maybe
So we can look at that. So how would I know if something is dimensionalized or non-dimensionalized? So what was I was in, so we're using step 2. I believe it's, so here we are. So here's, I can do help properties. And so here, when you see what the default value is and the current value is, you see that there's units attached to them. And so what you'll see is, like, for our shear modulus down here, it's converted pascals into the sort of pure SI meters, kilograms, seconds. Here's the validator, so it's got to be greater than 0. So the shear modulus, it won't let you put in a negative shear modulus. And it's converted my years to seconds. And it doesn't say 2 years here. It's the equivalent of 2 years in seconds. So when it read it in, it converted the years to seconds. So internally, everything is converted, and this comes back to why we put like 9.9999 years, is because it's converted years to seconds, and so there's, I don't know if it's exactly the number of seconds in a year, but it's there's additional round off there because internally it's converted everything to seconds, and then it non-dimensionalizes the seconds. So let's see, let's get back to running step 2. So that's where, right now, that's where you have to go to the manual in Appendix B that lists all of the components, and I believe they are grouped by category. That's the best, right now, that's the best place to look. Once we get the GUI interface, then it would tell you which ones you could, are available that would meet that. So here's our current error message. Here's our Python stack trace, so it's initializing our integrated elasticity. Here's our error message. Determinant of Jacobian is 1.25 times 10 to the minus 7 for cell 0 is smaller than minimum permissible value of 1 times 10 to the minus 6. The two most likely causes of this are highly distorted cells and non-dimensionalization with a length scale that is much larger than the dimension of the cells. So which of these is most likely to be the case for this example? Do we have distorted cells? They're pretty much exactly square. So length scale. So let's go back and look at our length scales. So what was our, I didn't mention it, but our cell size is 10 kilometers on the edge. And length scale current value is 1,000,000 meters. I think something's wrong there. The default was a kilometer. So let's go back to the default. And hold on, before I go too much farther, I want to save this file so I have a record of what errors I really want. So I need to go up. So we fixed this one and we fixed that one. Okay, so now we have could not find value left lateral slip in spatial database. Final slip. Available values are lateral slip, reverse slip, fault opening. So in some spatial database for the final slip, I put in lateral slip, but it was looking for left lateral slip. So clearly that's a pretty obvious fix, is to change the name of lateral slip to left lateral slip. So I go down here. Where's my spatial database for final slip? Here's final slip. So let's stick in left lateral. So some of our error messages are actually pretty much tell you what's wrong. So let's run again. So now here's our stack trace. Now we're initializing the constraints for the faults. Vertex with label 396 on negative side of faults. Fault external is constrained. Fault vertices cannot be constrained. So as Charles pointed out, normally when we have a fault and a Dirichlet boundary condition, we remove the fault vertices from the Dirichlet boundary condition node set. In this case, when I set out to do the problem, I was thinking I wanted my faults to be in the middle of the domain. So what I did is I used the wrong node set for my faults. So I used the fault that went through the whole domain, and I want to come back and I want to use just the node set that was for the faults, the embedded fault portion. So let's run again. Another error. Error computing orientation of cell face up direction 001 cannot be parallel to the face normal 001. If the face is horizontal, adjust the up direction parameter. So this is coming back to I'm trying to find the orientation of my fault. Remember, I have a vertical fault. It says I have a face that has a normal direction in the vertical direction. So this is a little difficult to picture, but the suggestion is adjust the up direction parameter. So let's just adjust the up direction parameter. So let's see. I need to add up direction, and I know that'll fix it. So we'll see what happens. Hey, it ran. Okay, so let's look at the output in ParaView. Yeah. So that way, I alleviated. I cheated. No, I just gave Pilot a hint on how to resolve the orientation of the faces. So if I look at the faults, let's look at the fault info, what the fault looks like. Whoops. That's a very interesting fault surface. Now you can see why I have a vertical fault surface, but I also have these little ledges. And you can see why, I thought things should have been working. If I have a vertical fault surface, I end up with horizontal faces in my fault surface. Let's look at, I do have the normal direction. So let's plot what the normal direction looks like. And you can see what Pilot did. You can see that it comes up with some pretty funky normal directions at this point. So on the vertical part, it comes up with the right normal directions. Here at this point, it's finding sort of the average based on area, weighted by area for, I want that to be a different color. Oops. There we go. So here's my normals. You'll see that normal's sort of crazy. So the issue is that what I really want my fault surface to look like, let me go back to, the purple is what my fault surface, my node set corresponds to. You'll notice that my fault basically extends one cell outside of what my intended fault surface is. That comes back to how we insert the cohesive cells. I forgot to mark my buried edge. And